Hello everyone, welcome back to Physics 331. So today we're going to do something a little bit different, and I'm going to try to record a little bit of a demonstration. And this is going back to thinking about some of the things we discussed about transmission lines, and in particular we're going to think about the frequency response of a transmission line. So if we send a signal through a transmission line, how does the signal that arrives at the far end depend on frequency? And so the way we're going to try to think about this, or with the way the demonstration is going to work, is we're going to use something called a vector network analyzer, or a VNA. A VNA is an instrument that's used in microwave electronics widely in research these days, and it's called a two-port device. So there's port 1 and port 2, and we're going to connect a long transmission line between ports 1 and port 2. The way we're going to use the VNA is port 1 is going to be our signal generator, so it's going to generate a signal, and then so that signal will travel the length of our transmission line. It'll arrive at port 2, which is going to serve as our detector. The way the VNA works is that port 1 has an output impedance of 50 ohms. The cable that we're going to use has a characteristic impedance of 50 ohms. And port 2, our receiver, has an input impedance of 50 ohms, or a load impedance of 50 ohms. And so if you remember our expression for the reflection coefficient, which we called gamma, if the load impedance ZL, which is the impedance looking into port 2, is matched to the characteristic impedance of the transmission line, Z0, then this difference in the numerator is 0, and there should be no reflection. That is, we should have a perfect transmission from port 1 to port 2. And what the VNA is going to do for us is it's going to measure that transmission coefficient. So we're expecting that if we had an ideal transmission line where the load impedance of port 2 was matched to the characteristic impedance of the coax, we should have perfect transmission, or a transmission coefficient of 1. So typically VNAs can be very expensive instruments, so tens of thousands of dollars. These days they're starting to develop affordable versions, and so we're going to use this VNA called Libra VNA. It goes from about 1 megahertz or to 6 gigahertz, and so it costs about $500. So here's a photograph of the apparatus that I have in front of me. I took this picture just a few minutes before recording the video. And so here's the Libra VNA. Here's port 1. It has a little blue cable coming out of it. But then we have our long coaxial transmission line that's coiled around and around and around. This is just like the cables we use in the lab every day, except it's long. It's about 8 meters long. And then it goes into port 2, and there's some software that's used with the Libra VNA to measure this transmission coefficient. Okay, and so what I'm going to try to do is I'm going to try to open that software, which I have running right now, and I think what I can do is show the taskbar. And so here is the software. What we're measuring is called S21. And what S21 means is it's a signal generated at port 1 and detected at port 2. So S21 is the transmission coefficient. The scale here is the magnitude of that transmission coefficient. So it could in general be complex, so it has a magnitude and phase. So we're just going to look at the magnitude. And it's measured right now in decibels, which is a log scale. So 0 decibels is a perfect transmission, transmission coefficient of 1. And then going down to minus 20 on this scale. Along the horizontal axis, we have frequency, And so down here, the lower end of our frequency range is, where is it shown here? 1 megahertz. And the upper end of our frequency range is 6 gigahertz. So we go from 1 megahertz up to 6 gigahertz on a linear scale. And so the green line is the measured transmission coefficient. And so what you can see is at low frequencies, the transmission coefficient is close to 0 dB or 1. But as we go higher and higher in frequency, this transmission coefficient gets lower and lower and lower. The decibel scale, the way you would convert, say, minus 10 dB, which is right here between 3 and 3.5 gigahertz, is the ratio of the power coming out of port 1. So maybe let's do it this way. The ratio of the power delivered to port 2 divided by the power coming from port 1 would be 10 raised to whatever the reading is in dBm, minus 10 in this case, divided by 10. So minus 10 divided by 10 would be minus 1, raised to the power 10 would be 0.1. So only 10% of the power is reaching port 2, 10% of the power that was output from port 1 is reaching port 2. So in other words, we've lost 90% of our signal when we reach somewhere around 3.3 gigahertz. And then down here around 6 gigahertz, it's not quite there, but it's approaching minus 20 dB. And so if we were to calculate that transmission coefficient in terms of a power ratio, it would be minus 20 divided by 10, which is minus 2, raised to the power of 10. Or 10 raised to the minus 2, so it would be 0.01. So out here, only about 1% of the incident power is actually arriving at port 2. And so everything we've talked about for transmission lines can't account for this effect. Our transmission line model was a bunch of daisy-chained LC sections. So there was some inductance per unit length and a capacitance per unit length, which we used to model our transmission line. But inductors and capacitors are lossless components, and so we can't explain this loss. If we were to measure the reflection coefficient, we would see that there would be very little power reflected back to port 1. So that's not an explanation. The power is being lost along the length of the transmission line. And so all of this is just to try to point out that our model of the transmission line that we discussed in class is an idealized model. It's incomplete. So the real model for an actual transmission line, non-ideal, is here would be our signal generator with an output impedance Z0. So that would be like port 1 of our VNA. Here is our load impedance ZL, so this would be like port 2 of our VNA. And then the complete model of the transmission line, it has our inductance per unit length L, and it has our capacitance per unit length C, and then we have these small sections of these LC networks of length delta X, so the inductance of this single section is L delta X, and the capacitance is C delta X. But now in our model, we include a resistance per unit length times delta X for this section, and a conductance per unit length times delta X. And this resistance and conductance accounts for the losses that we're seeing in our transmission line, and these effects get larger and larger as we go up in frequency. I'm not going to say too much about it other than that this resistance is due to conductor losses along the transmission line length. And so this is the usual Joule heating, where if you have some resistance, you pass a current through it, you dissipate power I squared times R. The conductance corresponds to losses in the dielectric, where for our coaxial transmission line, the dielectric would separate the center conductor and the outer conductor. And so it's typically Teflon in usual coaxial conductors. And so the Teflon will have a dielectric constant, and then it could have that, I guess it has a permittivity, and so the permittivity has a real part and an imaginary part. The real part roughly corresponds to the dielectric constant, and the imaginary part corresponds to dissipation of power in that Teflon material that separates the center conductor and outer conductor. And so if you make some physical models for what this resistance per unit length and what this conductance per unit length should look like as a function of frequency, then you can try to explain or to fit the frequency dependence of that transmission, that transmission coefficient that we just looked at on the VNA. Okay, good. So that's all I wanted to say. Thank you very much, and we will see you next time.